In this video, we are going to discuss the first three questions of the question paper 4-1 of 9701 chemistry, that is A levels chemistry of the examination series May-June 2025. So here is our first question, which says the both calcium carbonate and barium carbonate decomposes when heated to form a metal oxide and a gas. Okay, write an equation for the thermal decomposition of calcium carbonate. Now very simple and straight is that the thermal decomposition of calcium carbonate forms calcium oxide and the CO2, that is carbon dioxide gas. So here we complete the equation by simple straight equation which is already balanced. Now if we go ahead with B part, state which of the calcium carbonate or barium carbonate decomposes at a lower temperature and explain your answer. The compound that decomposes at a lower temperature. Now if we know the trend of group 2 carbonates, then group 2 carbonates, the thermal decomposition temperature increases down the group. That's, you can say, the thermal stability increases down the group. So if we are talking about a lower temperature, then we can say that it is calcium carbonate, because barium carbonate decomposes at a higher temperature. Now the explanation for this is that the Ca2 plus has lower cationic size, or you can say smaller cationic size, Now because of that, what happens is that the ion polarization of CO3 2 minus is greater by Ca2 plus compared to Ba2 plus, which has a greater ionic radius. So if the ion polarization of CO3 2 minus is greater, the CO bond, you can say the CO bond is weaker and hence decomposes at lower temperature. So it doesn't need a very high temperature or high heat to break down, because the ion polarization of CO, which is higher for calcium, which is lower in cationic size, this makes the CO bond a little weaker, and because of the weakness it breaks down very easily and decomposes into calcium oxide and carbon dioxide easily, right here. So if we go ahead with C, calcium oxide reacts with water to form compound A. Now barium oxide BaO reacts with the water to form compound B. Identify A. Now if calcium oxide reacts with water, it's going to form calcium hydroxide, CaOH types, calcium hydroxide. Now explain why A is less soluble than B. Now this is directly related to the solubility of hydroxides of group 2, that is calcium hydroxide and barium hydroxide. Now we should know that the solubility of hydroxide increases down the group 2, that is barium hydroxide is more soluble than calcium hydroxide. Now the reason being is that, again, as the cation size increases, the delta H lattice and delta H hydration both decreases or both becomes less exothermic down the group. So both goes less exothermic. Now what does that mean? That the delta H lattice and delta H hydration is more exothermic for Ca2 plus, right? That is calcium hydroxide, I'll say calcium hydroxide. Delta H lattice and delta H hydration is more exothermic for calcium hydroxide than barium hydroxide. Now what happens down the group is both decreases down the group, but delta H lattice decreases by a greater value. So because of that, the difference in the enthalpy of lattice, or you can say difference of the delta H lattice, is greater than the delta H hydration down the group. Now because of that, what happens is that delta H solution is less exothermic for calcium hydroxide compared to barium hydroxide. Now if it is less exothermic, then obviously it is less soluble, because for a compound to be soluble, the delta H solution has to be negative, that is exothermic, or more negative for being more soluble. So this is how you're going to write explanation in the 3 marks. So what is important is first explain the cation size, then explain the trend in delta H lattice and delta H hydration. Then explain the difference between these when we go down the group, and then explain that delta H solution is less exothermic, that is less negative, and that's why it is less soluble. These 3 important points are necessary to cover in 3 marks. Here we go with the question 2 here, where it's 3 experiments are carried out to investigate the reaction of nitrogen oxide NO with chlorine. So here is the equation given, where nitrogen oxide reacts with chlorine to form nitrosyl chloride. The rate equation for this reaction is shown here, where the rate is equal to rate constant to the concentration of NO power 2 and in the multiply by the concentration of chlorine. Now under the conditions used in experiment 1 and 2, the value of K given is 26.4. Understand, this is the value of K given here, that is 26.4. Now the rate of the reaction is measured in mole per dm cube per second. Now state the unit of K. Now if we rearrange the K to get the subject, then we have rate upon the concentration of NO to the power of 2 into the concentration of chlorine. Now if rate is measured in mole per dm cube per second, but the concentration of NO to the power 2 has to be mole square dm power minus 6, and the concentration of chlorine is again moles per dm cube. So this directly gets cancelled off, and so whatever we are left with is this and the second. So we can write the unit of as mole power minus 2, dm power 6 and seconds power minus 1. You can rearrange this here. dm cube can be written in front and the moles can be written later on, so that all the negative term can be written together. So what's the next part? Next part 2 here. In experiment 1, the initial concentration of NO, nitrogen monoxide, and chlorine are equal. The initial rate of reaction in experiment 1 is 2.57 into 10 power minus 6 moles per dm cube per second. Now this is about initial concentration are equal, it's written, and the initial rate is given. Now calculate the initial concentration of NO, show your working. Now the value of K is already given here, that is 26.4. So if we write a rate equation as rate is equal to K into the concentration of NO to the power of 2 into the concentration of chlorine, then here we end up with this equation, where we can substitute the value of 26.4 for rate constant, and it says that both of the initial concentration are equal. Now this is important. So if we take that as X, then for NO we can write it as X square, and for chlorine we can write it as X. Now they have already written that the initial rate is equal to 2.57 into 10 power minus 6. So 2.57 into 10 power minus 6 we can write here. So calculate the value of x. Now x, if we want to find out, then it is the cube root of 2.57 into 10 power minus 6 upon 26.4. So here we end up with the equation. Finding the cube root of this whole value, we can write it as 4.59 into 10 power minus 3. Now that's the concentration of nitrogen monoxide NO, which we had taken as x, and as both of the concentration was same, so the concentration of chlorine can also be taken as x, and so we calculated the value of x to find out the initial concentration of nitrogen monoxide NO. Now the third part is in experiment 2. The initial concentration of nitrogen monoxide and chlorine are both 10 times greater than the initial concentration used in experiment 1. Calculate the initial rate of reaction in experiment 2. So again, if we write rate is equal to the value of K, that is 26.4, and now into the concentration of nitrogen monoxide and chlorine, but then as I said, it is 10 times greater. Now we have got this value as the initial concentration, so if we multiply that with 10, then we have 4.59 into 10 power minus 2 rather than 10 power minus 3 here. So now if this concentration is both for nitrogen monoxide and chlorine, then it has to be go into the power of cube. So if we substitute all these values and find out, then we get as 2.57 into 10 power minus 3. So this is the rate. We calculate 2.57 into 10 power minus 3 moles per dm cube per second. So here we calculate the initial rate of reaction for experiment 2. The second, that is the B part. Next is experiment 3 uses a large excess of NO, nitrogen monoxide, and the initial concentration of chlorine is 2 into 10 power minus 4 moles per dm cube. The graph of chlorine against time shows that the reaction has a constant half-life. Explain this observation. Now, if we have drawn the graph for the concentration of chlorine against time, so we are talking only about the change in the concentration of chlorine and nitrogen, not nitrogen monoxide. And as such, the nitrogen monoxide concentration is a large excess. Now, what does that mean? If it is a very large excess, then over time, the concentration of nitrogen monoxide does not change. It remains almost constant. So we are taking only the chlorine in consideration and against time. And if we have got constant half-life for that, that shows that the order of reaction, with respect to chlorine is first order. That's why we get the constant half-life. If the half-life increases over time, then it is second order, and if it decreases, then it is zero order with respect to chlorine. But as it's written constant half-life, it is first order with respect to chlorine. So that's what we can observe and explain here. And if we talk about NO, then we can just add that the concentration of, or we can write it in short, the concentration of NO remains constant, remains almost constant throughout the reaction. That's it for the 1 mark explanation. Now for the 2, under the conditions used in experiment 3, the value of rate constant is 105.6. Now understand, this is the experiment 3 and the rate constant value has changed under these conditions. Now show that the T half of chlorine is 6.56 into 10 power minus 3 seconds under this condition. Now if we have got the value of rate constant, then we can directly use this formula as T half is equal to 0.693 upon K. This equation can be used only for the first order reaction, and if we have already proved that chlorine has got the first order for this reaction, so directly substitute the value as 0.693 upon the rate constant value, that is 105.6, and we get the same value as 6.56 into 10 power minus 3. So this is the value we get in seconds. The third part is calculate the time taken in seconds for chlorine to fall down to 1.25 into 10 power minus 5 moles per dm cube in experiment 3. Now it's a concentration we are talking about which has fallen down to 1.25 into 10 power minus 5. Now let's see what is the initial concentration of chlorine given is 2.00 into 10 power minus 4. Now you can understand that if it's falling down to 1.25 into 10 power minus 5, that shows that it has fallen down from 2.00 into 10 power minus 4 to 1.25 into 10 power minus 5. So it has decreased 4 times. You can say it has decreased 4 times because it goes 1, then it goes to 0.5, and then it goes to 0.25, and then it goes to 0.125. So that is 4 times decrease. 1, 2, 3, 4. 4 times it has decreased. So concentration decreased 4 times. So even the time T half also decreases 4 times. So what we have to do is 6.56 into 10 power minus 3 is the only one time you can say T half. Now it keeps on going on, so multiply by 4 because 4 times time will be taken to decrease its concentration to 4 times. So the T half has to be multiplied by 4, and so we get the answer as 2.62 into 10 power minus 2 seconds. Multiply the T half by 4 times. Why? Because the concentration has decreased 4 times to its half, right? So then you can write is 2.62 into 10 power minus 2 seconds when we multiply the T half by 4 times, right? The C part is sulfur dioxide SO2 reacts very slowly with oxygen in the atmosphere, forming sulfur trioxide. Now this is the oxidation of sulfur dioxide with oxygen to sulfur trioxide SO3. This reaction is much faster in the presence of NO, that is nitrogen monoxide. Explain the role of NO in this process. Now if any substance is increasing the rate of reaction, making it faster, then obviously it is acting as a catalyst. So what we can write is that NO is a catalyst as it increases the rate of reaction, Now it's written include the chemical equations in your answer. So in that case we can write NO reacts with oxygen to form NO2. Now if we balance the equation, we get 2 and 2 here. The NO2 then reacts with the sulfur dioxide to form sulfur trioxide and NO, that is nitrogen monoxide again. So we can say that the NO is regenerated. So we can add that sentence here that the nitrogen monoxide is regenerated, that's why it acts as a catalyst. Now if we specify here the catalyst, then we can also write that it is a type of homogeneous catalyst. Why? Because the reactants are also gases, and the reactants are oxygen and sulfur dioxide, they are also gases, and the nitrogen monoxide and nitrogen dioxide are also gases. So as all these three of them are in the same phase, then they are homogeneous catalysts. So we can be specific that the nitrogen monoxide is a homogeneous catalyst as it increases the rate of reaction and is also regenerated. And these are the chemical equations present, which is showing that the nitrogen monoxide is a catalyst. Now let's go ahead with question 3 now. Here is question 3. So A part is the chromium 3 hydroxide, that is CrOH thrice, is only slightly soluble in water. The value of the solubility product Ksp of chromium hydroxide is 1.0 into 10 power minus 33 at 298 Kelvin. Now complete the expression for Ksp of chromium hydroxide and include the units. Now if we have chromium hydroxide as the formula here, then we can write the equation like Cr3 plus 3OH minus. Now if we have Cr3 plus, then the concentration of chromium ion, that is Cr3 plus, has to be included, and the concentration of hydroxide ion has to be included to the power of 3, that is cube. Why? Because we have 3OH minus ions. And now if we work out the units, then for the concentration of chromium ions we have moles per dm cube, and for hydroxide ions also moles per dm cube, but then again to the power of 3. So if we count all this, then we have mole power 4 dm power minus 12. So these are the units and this is the Ksp expression. And let's go ahead with the second part. It is calculate the solubility in grams per dm cube of chromium hydroxide in pure water at 298 Kelvin. Let's first find out the solubility in moles per dm cube, and then let's go ahead by converting it into grams per dm cube. So if we have a look here, the Ksp value is a 1.0 into 10 power minus 33 is the Ksp value. So here we have substituted that value in the Ksp is equal to chromium and hydroxide and concentration multiplication, that is product has to be there. So if we take the solubility of chromium in X as X, chromium ion, then for hydroxide it has to be 3x to the power of 3. Now the reason is that the chromium and hydroxide ion, as we have written in the equation up here, is ionized in this form, that is 1:3 ratio. So if the solubility of chromium hydroxide is X, after after going into the aqueous solution, it will be split or ionized into X and 3x form, because it is 1:3 ratio. So substituting the concentration of both the ions, here we get this value. So in that case, now we have 27 into x power 4, and that is equal to 1.0 into 10 power minus 33. Now if we find out the value of x, then we get as the value of x can be calculated by 4th root of 1.0 into 10 power minus 33 upon 24. That's what we calculate by equating the equation, and we get the value as 2.47 into 10 power minus 9 moles per dm cube. That's the solubility of chromium hydroxide in moles per dm cube. Now we need to change it into grams per dm cube, and for that we'll have to multiply by its mr. Now what is the mr of chromium hydroxide? We can calculate that in the rough, and we get the value as 103. So if we find out the solubility in grams per dm cube, we need to multiply 2.47 into 10 power minus 9 into 103. So if we again find the product, we get as 2.54 into 10 power minus 7. So this is the value of solubility of chromium hydroxide in grams per dm cube. Remember, this part is very important because there are full chances that the students might forget multiplying it by mr to change the solubility in grams per dm cube. So here the third part is chromium hydroxide is less soluble in 0.100 moles per dm cube of NaOH than it is in pure water. Now the reason is because of common ion effect. We can directly write because of the common ion effect. Now what is a common ion effect? If we add any ion in common, that is either chromium or hydroxide, in a saturated solution of chromium hydroxide, then the solubility decreases because the highest concentration which can dissolve is 2.54, or you can say 2.47 into 10 power minus 9 moles only. Now OH hydroxide ions is added, that decreases the solubility, and that's why we say the solubility is less in 0.1 moles per dm cube NaOH. Let's see with the B part. The value of the acid dissociation constant Ka of butanoic acid is 1.51 into 10 power minus 5. Calculate the pH at 0.1 moles per dm cube of butanoic acid at 298 Kelvin. Show your working. Now if we calculate the concentration of H plus first, we have the formula as Ka into the concentration of acid, that is Ha. So if we substitute the value of Ka is given here, which is 1.51 into 10 power minus 5 given here. This is the value, and the concentration of acid is given here, that is 0.100. So that's the root, and so the concentration of H plus here is 1.23 into 10 power minus 3. Now that's the concentration of hydrogen ion, and so the pH is equal to minus log of the same value, that is 1.23 into 10 power minus 3. And if we find out the pH log value, it is 2.91. So that is the pH, 2.91. Simple substitution of an formula. The second part is calculate the pH of 0.1 mole per dm cube of NaOH at 298 Kelvin. Now if we calculate the pH of a base, we can directly use the formula as pH is equal to 14 minus POH, or we can indirectly use the formula as Kw is equal to H plus concentration into the hydroxide ion concentration also, where the Kw value is 1 into 10 power minus 14, and the concentration of hydroxide ion is given here, and so we can find out the value of H plus from here, and then we can find out the pH, and we can do directly this one also, where it is 14 minus log of hydroxide ion. So that also can be done. So if we substitute this value, we have 14 minus of 1, because minus of hydroxide ion, that is 0.1. if we substitute here, let me write it fully here, 14 minus log of 0.1, and so we get as 14 minus 1, and so the pH is 13. I hope it's very clear. We can do it as 14 minus POH. POH is what? Minus log of hydroxide ion concentration, which is 0.1 given here. 0.100 concentration of NaOH, which we substitute here, so we get 14 minus 1, that is 13. Or we can substitute the concentration of hydroxide ion here in this expression, where it is 1 into 10 power minus 14 Kw, 0.1 for hydroxide, so we can find out the concentration of H plus and then substitute it in pH expression. That also can be done. Now the third part is 5 centimeter cube of 0.1 mole per dm cube NaOH is added to 10 centimeter cube of 0.1 moles per dm cube of butanoic acid. Calculate the pH of the resulting solution. It's clearly written, show your working. Now let's understand what is happening here. Butanoic acid, I can write it in short HA plus NaOH, that's reacting to form the salt, that is NaA, that is sodium and the butanoic acid and the water, and we can understand it is a 1:1 ratio because the salt formula will be CH3CH2CH2 COONA. This is the formula of the salt, which I am not writing here. I am writing the formula of the salt in short like this. So if we take the initial concentration of the butanoic acid, then it is 0.1, and the volume is 10 centimeter cube. So if we change it into dm cube, it is 0.01. Now if we multiply these two value, the moles of the acid turns out to be 1 into 10 power minus 3. I hope it's very clear. I'm changing the volume and concentration into moles because moles is equal to concentration into volume. So here 0.1 into 0.01, which gives us 1 into 10 power minus 3. Same here, if we implement, it is 5 into 10 power minus 4, because here again we multiply the volume and the concentration. 5 into 10 power 5 centimeter cube into 0.1 is 5 into 10 power minus 4, because here also will change it into dm cube, which is 0.05. Yes, no, it's 0.005, right? So we get this. Now if both of it react, the moles of salt is going to be 5 into 10 power minus 4, because it's the limiting reagent that will change into the salt with 1:1 ratio. So what is the acid left over? Now out of that 5 into 10 power minus 4 moles of acid will be used up because of 1:1 ratio. Then the leftover acid is 5 into 10 power minus 4. So moles of the acid left is 5 into 10 power minus 4. The moles of salt is 5 into 10 power minus 4. So we can say that the concentration of both the acid and salt is same, 5 into 10 power minus 4. Correct? Now if we take up the pH, you can say formula, then we will say H plus is equal to Ka into the concentration of acid upon the concentration of salt. And if we substitute the value of Ka of butanoic acid, which we can see here, that the value of Ka of butanoic acid is 1.51 into 10 power minus 5. Let's substitute that. 1.51 into 10 power minus 5 into 1. Why? Because the concentration of acid salt are same, so the ratio changes into 1. So H plus concentration is directly equal to the Ka value, and if we substitute that value into the expression of pH, that is minus log of 1.51 into 10 power minus 5, we get the pH as 4.82. So this is how we calculate. I hope my rough working here to show that the acid and salt concentration are same. I hope that's clear. So we substituted that into the Ka expression to find out the concentration of hydrogen ions. Here this is the last part. See, 80 centimeter cube of an aqueous solution containing 0.704 gram of butanoic acid is shaken with 100 centimeter cube of benzene. Now benzene is a solvent. Remember, aqueous solution, that is water, is another solvent in which we are adding butanoic acid as a solute. So solute is butanoic acid. There is 0.556 gram of butanoic acid in 100 centimeter cube of benzene at equilibrium. calculate the partition coefficient Kpc of butanoic acid between benzene and water. So first write the expression of Kpc, that is partition coefficient, as the concentration of butanoic acid HA into benzene, that is organic solvent, upon the concentration of butanoic acid in the aqueous solvent, that is water. Now understand, the volume of benzene is 100 centimeter cube and the volume of water is 80 centimeter cube, and it's written that 0.556 gram of butanoic acid was found in benzene. Now the total gram, that is total mass of benzene, was 0.704 at the starting. So what is left over in the water, that is concentration of HA in water is 0.704 minus 0.556, that is 0.148. Now if we substitute this, we directly, rather than moles, you can use mass, because mass upon mR is moles, and mR of both the numerator and denominator will get cancelled. So mass can be used in the numerator and denominator directly. So in the organic solvent, the mass of butanoic acid is 0.556 divided by its volume, because this is concentration. Moles upon volume is the formula for the concentration. So 0.556 divided by the volume of benzene as a solvent is 100, divided by the concentration of acid in water. Now what is left in water is 0.148 grams. So 0.148 gram divided by its volume, which is 80 centimeter cube. So 80. Now if we substitute all these values, we get 3.01. 3.01, that is the partition coefficient of butanoic acid in benzene and water. Kpc never have a unit because it's the concentration upon concentration, so the units gets cancelled off, and so it has no unit. So here our question 3 ends. The remaining questions we will discuss in the next video.